Hello, Jake the Foxy here, coming at ya with another plasma video. Now, some of you might have heard about a little thing called Conway's Game of Life, which is basically this famous zero-player game that is well known for creating complex and intricate patterns out of a very simplistic set of rules. Now, I'm not here to talk about that in this video. Rather, what I want to do is try and shed some light on a similar sort of game which I believe deserves some more attention, namely Langton's Ant. Now, in this game, you basically start out with an ant on an infinite game board. And every turn, the ant will look at the space that it is on. And if the space is colored white, the ant will turn to the right. And it will color the space black before moving forward. Conversely, if the space is colored black, then the ant will turn to the left before coloring the space white and then moving forward. So the state of the game board is constantly changing as the ant moves around. So you can imagine that this leads to very intricate and complex patterns and behavior. Now, I have taken this general concept and expanded upon it in order to implement it here inside of Plasma. So, without further ado, why don't you check this out? So over here, we have our ant, which is actually a flying ant, as you can tell. But that's okay, it's still an ant. It's actually made using a drone for its body, which I find doubly humorous, because most flying ants are drones. Go figure. And you can see it has these spindly legs here, 6 of them, and these don't actually move or anything. They're just purely aesthetic to help it look more like an ant. Same here with these 2 little antennae. And it also has these 2 LEDs in the front for eyes, which actually change color to indicate the status of the ant, which I thought was kind of cute. And if you come around here to the back, you'll notice that there are several components on the ant's back, including a controller for its brain, a GPS unit, so that it can always know exactly where it is relative to the world grid, which is very important, which I'll get more into later. It also has a transceiver, so it can communicate with this 7-segment display that I set up way over there, so that it can keep track of the number of steps that the ant has taken. It also has this DMD dot matrix display, which just displays the current status of the ant, which is very useful for debugging, which is kind of an odd concept, debugging a bug, but that's still something that I had to deal with. It also has these two components on the bottom here, which are very essential. Basically the color sensor and the color painter, as these allow it to both read and write to the individual cells of the grid, which is what allows it to run the Langton's ant program. It also has these spotlights on the bottom here, which I added to allow it to more easily read the color of the cells at night. I don't know if that's strictly necessary or not, but I thought it looked cool, so I decided to keep it in. It also has this single solitary button right here in the back, that if I were to press that button right now, it would just go ahead and fly off and start doing its thing. But I'm not going to do that just yet, because I actually want to do things a little bit differently in this video. I'd rather show you the sketch for this machine first, before showing you what it actually does, because I think it's kind of important to know how it's actually doing what it's doing in order to truly appreciate what it does. So, without too much rambling, let's go take a look at the sketch. So this is the sketch for our ant. Now, Langton's ant is actually a very simple algorithm, but actually trying to implement that within Plasma turns out to be surprisingly hard. But I'll try my best to walk you through it. And it all starts up here with this section right here. And this whole section runs only once at the very beginning when the sketch is first initialized. And basically what it does is that it reads several different GPS tags that are each located in a different position on the board that the ant actually traverses. And it stores the location of those markers in each of these different global variables. And it uses these in order to compute where the ant actually is located within the grid. So I can assure that the ant always stays in line with the grid. And because the grid never moves, it's perfectly fine for us to read the GPS trackers only once at the beginning and then store their locations so we can access them later. And that's what this whole section does. Now, moving on over here, this section, this is actually the most complicated part of the entire sketch. This is the flight control system, because if you think about it, the drone object within Plasma does not know how to interpret commands like move forward or turn right. So I actually have to implement those commands myself so that when the algorithm issues those commands, the drone can actually follow them. So I have these different PID controllers here, each controlling a different thruster on the drone, like the longitudinal thruster, the vertical, and the yaw. And the PID controller stands for proportional, integral, and derivative. And if you don't know what that is, it's basically just makes it so that the motion of the drone is smooth, so it can move in a continuous fluid manner and not be jerky. That's really important in order for gaining fine-tuned control of the drone, which is what we need in order to keep the drone aligned with the grid. And all of that, controlling the PID controllers themselves, are all being controlled by this central flight control unit, which is basically one giant Lua node. If we look at the source code for the flight control unit, you can see that it's really messy, and I apologize for that. There's all of these global variables here which are used to keep track of the drone state, its target position, and its current position, as well as several other things that it needs to keep track of. Here's some initialization code which just copies the values from those global variables I mentioned earlier and stores them inside the Lua code so they're just easier to access. Here's something where you can set the state of the drone so it can update what it's actually doing, and it also informs the rest of the sketch about the change. And here's some special functions for recentering and rotating. And here's the main function right here, the update. This is the function that gets called every tick, and it basically does a little bit of math that's helpful here, but the main thing it does is that it has just this major switch statement here, which basically calls the corresponding function that it needs to perform based on the drone's current state. And each of these states each have their own function, such as looking at the target or going to the target, starting travel, and stop. There needs to be a special state for stopping all movement. One for recentering, and so on and so forth. Changing elevation. And I don't think even all of these are even used by the drone, and it took an awful lot of work to try and actually get this working, so unfortunately I wasn't able to actually go through all this code and clean it up, so again, I apologize for that. Fortunately though, you don't really need to worry about that, because the part of the sketch that is actually responsible for implementing the Langton's ant algorithm is right here, and it thankfully is much simpler. It all starts over here with detecting a stop event from the flight controller, because once the flight controller has stopped moving, it is then ready to process the next state of the Langton's ant algorithm. And it has to go through this timeline right here, because it is important that it reads the data from the color sensor before it invokes the on-step event for the Lua program. Because if it doesn't do that, then the program will have the wrong color information and it won't be able to follow the algorithm correctly. It also sends out a signal on the transceiver just so that the numeric display can show the total number of steps that have been taken. But everything happens all right here on the on-step event inside the Lua program. So let's take a look at that now. So looking at the source code, we can actually see the implementation of the Langton's ant algorithm. Now it starts out with a bunch of global variables here, and it creates this palette as an array of colors, which are all of the default colors that you get within Plasma. Now, the default Langton's ant algorithm only uses 2 colors, but we can certainly opt to use more than that. And we need more than that if we want to have multiple ants running at the same time. It also stores the grid position of where the ant is located within the grid. Now, notice that this is not in world space coordinates, but in integer grid coordinates. So 1 means 1 space up, and 1 over here means 1 space down and to the right. And there's also a couple of vectors here that just help with some of the math, but you don't need to worry about that too much. There's also this initialization function here, which reads in some of the default variables, which we'll talk about a bit later. And there is this function, which is responsible for actually reading the cell that the ant is currently hovering over. It basically works by first using the color sensor to read in the color data, and then finding the index of the palette that corresponds to the matching color. And the reason why we have to do it this way is because the color data that we get from the sensor might not match the color we're looking for exactly, so we return the closest matching color instead, which is what allows the function to work. And then here we have a few basic functions for movement, which uses those tables I showed you up there for rotating right, rotating left, and rotating 180 degrees, as well as moving forward. But down here, this right here is the most important function. This is the on-step function, which is called every time the algorithm updates, and this right here is the Langton's ant algorithm. Exactly. It first reads the cell, and based on what color it sees, it either turns the cell to the ant's color and then rotates left, or it turns the color back to white and then rotates right. It also has this special condition right here, such as if it runs into the border of our grid, it turns around 180 degrees. So that way the ant actually stays confined to our grid and doesn't just wander off the grid and go off into space or something. But this is the Langton's ant algorithm right here. So if you want to play around with this yourself or change it so that the ant actually follows different rules, this is the function right here that you want to change, the on-step function. So there's only one section left, and thankfully it is fairly straightforward. The only thing that it does is control the left and right eye LEDs on the ant to indicate the current status. It reads in the status from the flight controller with this state changed event, and it basically uses a mapping function here to give the eyes a different color based on what state it has. It also displays the state on the LCD screen, which I showed earlier. And that's it, basically. Now, there are also a set of different variables that the sketch uses to keep track of various different things that are important to the ant, as well as a few different global constants. But the ones that you are probably the most interested in are only 3. The first of which is my color, which is just an index into the array of colors that I showed you earlier. And that's used to select the specific color that the ant will use to color the on position for the cells. The off position is always white for all of the ants, but by having a different on color for each ant, you can actually use that to track the movement of each ant over time to see where each of them go. The other one here is my height, which determines how high the ant will hover above the grid in meters, which is important for keeping the ants from flying into one another. I found that a height of about 3 meters looks nice if you're only using a single ant. And finally, there are the start X and start Y variables, which is just containing a position on the grid where the ant will actually start from. By default, this is just set to 00, which is the exact center of the grid. But if you wanted the ant to start somewhere else, like if you are using multiple ants and you need them to start in a different location from one another, then you can set that here. And that's basically all that there is to the Langton's ant sketch. So, now that we've seen what the sketch looks like, let's see what this thing can actually do. Now, if I just press this button right here in the back, you'll see that the ant immediately flies off and starts to recenter itself right in the center of the grid. And as soon as it reaches the origin point, it will stop and begin to lower itself. See, right now you can see it, the display says it's currently recentering. And sometimes takes a bit because it tries to be very precise. And see, now it got it, and now it's lowering down to the height that we specified within the sketch. And once it reaches that height, it'll stop, and then it will begin to reorient itself to align with the hexagonal grid. So that way it always stays in line with the grid, and it always starts out facing the same direction, which is important for consistency. And as soon as it finishes doing that, it's basically done and is ready to start running the algorithm. See, there it goes. It just colored that tile orange because it was white, and it did the same thing here, and it's now turning to the left because it was white. And if we see that over here, it'll do the same thing again. It does take it a little bit of time because it's trying to be very precise. It needs to be to stay in line with the grid. And see, now it's turning right again. Now, if I go ahead and turn this tile orange, then because it's already orange when the ant gets there, it should turn it white and turn to the right then. See, there it goes. And if I do that again, you'll see it do that another time. And it basically just keeps on doing that forever. That's the Langton's ant algorithm. Now, there are a few slight differences between what I have implemented here and the actual traditional Langton's ant. Traditionally, the game is played on a square grid, but I've opted to go with hexagons here because I can do that, and hexagons are the bestagons. And I really like the sorts of patterns that can appear in the hexagonal version of Langton's ant, which I hope to show you later in the video. Another slight difference is that in the actual Langton's ant, it's supposed to be played on an infinite grid, but because this is plasma and I don't want to lag my computer to death, I actually had to settle for going with a finite grid, which is why we have this black boundary over here on the edge. The algorithm actually treats this as a special color, separate from the white and the other colors, so that when the drone sees this color, it knows, oh, I'm on the edge, so it turns back around 180 degrees and heads back into the playing field. So that just keeps the ant from wandering off the grid and stays confined to the playing area that we've specified here, which isn't really a problem in practice because a single ant can go for thousands of steps before it ever encounters the edge. I made sure to make the playing field big enough for that, at least. I could have potentially made it even bigger, but I was already getting performance issues just having it this big, so I didn't want to stretch it any further than that. I also created this special counter over here to keep track of the number of steps that the ant has taken. So you can see it's already taken 11 steps since we started it. Now, there is a 7-segment display component that is available to use in builds. But as you can see, this one is tiny, and I wanted one that could be seen from a great distance away. So I had to make my own 7-segment displays out of these LEDs. And I think it worked out rather well. It's fairly straightforward. I won't bother showing the sketch, but it wasn't too difficult if you know how. And that's basically it for Langton's ant. Now, you don't have to just sit here and watch it go at this incredible snail's pace. Instead, you can just watch this time lapse that I've already prepared for you. So, now that you've seen what a single ant is capable of, what do you suppose would happen if we unleashed an entire army of ants? Now, I've lined up 6 different ants here, each of a different color. And if I press the buttons on each of their backs, they will each fly off in turn to their designated location within the game board and start doing their own thing. And the reason why I made them each a different color is to not only to keep track of the ants, but also so that each of the ants can color the tiles on the board according to their own color. Now, normally in the Langton's ant game, you only have 2 different colors, black and white. But I've set things up here so that all of the ants treat white as turning to the left, and they treat every other color, except for black, as turning to the right. This way, if an ant will come across the path of another ant, it will treat it exactly the same as if it intersected back upon its own path. So all of the ants can weave in and out between each other and wind up interfering with each other's paths, which should hopefully lead to some pretty interesting results. And as you can see, some of them have already started already. Here with orange painting the ground orange just like before, and blue painting things blue, green green, and so on. And so in this way, you can not only keep track of where each ant currently is, but also where each ant has been based on the colors that are present on the map. Now, when I first started pondering how to handle the multi-ant situation, I was greatly concerned about the possibility of collisions, like what would happen if 2 ants were to bump into each other physically. That might cause them to veer off course and become misaligned with the grid, and that could create all sorts of problems. So I started wondering if maybe I should install extra sensors on the ants so they can tell if any other ants are in the near proximity, and then try to decide whether or not the ants should wait to let them pass or if they should do something else. And are just worried about this whole big mess of how to handle all of that within Plasma and in the Scratch. But then I realized, hey, this is a 3D game. I can just have each ant hover at a different height above the playing field. And then it's impossible for the ants to actually collide with each other. You know, sometimes you tend to over-engineer things, and you can't see the obvious solutions that are staring you right in the face. But once I decided that each ant should hover at its own designated height, the only thing that I had to worry about is, okay, what should I do if 2 ants overlap each other? That is, if 2 ants are trying to occupy the same cell on the grid. And fortunately, the ants already have a couple of sensors installed in them pointed straight down, which they use to both read and write to the grid cells. So I was able to use those exact same sensors to detect the presence of other ants. I didn't need to install any extra hardware for the multi-ant case. So then the only problem I had to worry about is, okay, what do I actually do if 2 ants were to overlap each other? Now, there are a couple of possible solutions to this. Like, I could have them just stop and wait until the ant below them moved out of the way, or I could have them do something else. But I realized that no matter what I did, that it would cause the ants to interfere with one another and actually change the pattern that's being created. So unfortunately, there's just no way to get consistent results in the multi-ant case. But so I decided to just go along with the simplest solution, which in this case just turned out to be treat it exactly the same as you treat the border of the map. So as soon as an ant detects that it has seen the border below it or another ant, it will just turn around 180 degrees and go back the other direction. And this actually works out pretty well if you think about it, because if the ant is turning around and going the other way, then it's less likely to intersect the path of the other ant in the future. So hopefully that leads to less collisions overall. And I don't know how good of a solution that actually is, but it seems to work well enough. And trying to do anything else would have made the sketch and the Lua code much more complicated. So I just decided to go along with this. Now, as before, you don't actually have to sit here and watch all of these ants progress along at a snail's pace. Once again, I have prepared another time lapse for you, so let's go and look at that right now. So, by now, you ought to be able to see just how chaotic things can get when using multiple ants. When they first start out, they all just sort of do their own thing, drawing identical shapes in their corner of the map. But as soon as one ant crosses another's path, it very quickly devolves into chaos. And unlike the single ant version, having multiple ants is non-deterministic, in that it depends entirely upon the order in which you start each ant, and to a lesser extent, the timing with which you start each of the ants, as both of those things can have a impact on the pattern, which can cause drastically different changes to compound in this chaotic system. With the single ant version, though, it's completely different. It's entirely deterministic in that as long as you start with the same starting conditions, like a completely blank board, then it will generate the exact same pattern every single time. And that actually is something that you can experiment with if you want to try out doing different things with these little ants. You can try painting different images on the ground and seeing how the ants interact with and change those images. Another thing that you could do is try changing the actual rules of the game. Like, if you see one color, then you wind up turning one space to the right. But if you see an entirely different color, then you wind up turning two spaces to the right. And that difference in rule set would wind up creating a completely different pattern. There are a few different rule sets that you can find online for Langton's ant, both the hexagonal and the square-based versions that produce some really distinct patterns, so it's worth looking into. But I think that's probably enough for one video, as I don't want this to drag on forever. So I hope you enjoyed this little look into Langton's ant, one of my favorite cellular automata. And with that, I'll see you guys next time. Bye for now!